Title: From Microemulsion Phase Diagrams to Hydrophilicity and Hydration-Controlled Adsorption. A Dissipative Particle Dynamics Modeling Study of Phospholipid Assembly in Bio-Oils. The introduction of this scientific paper provides an overview of the study's focus on the assembly and adsorption response of a ternary bio-oil phospholipid water system using dissipative particle dynamics (DPD) simulations. The main objective is to understand the large-scale self-assembly response of dipalmitoylphosphatidylcholine (DPPC) phospholipids in a model bio-oil solvent, triglycerides, in the presence of varying amounts of water. The researchers aim to obtain reverse micellar and microemulsion assembly phase diagrams of the ternary mixture and verify the model against existing literature data. The significance of the study lies in the accurate prediction of the large-scale assembly response and morphology changes, including adsorption response, in terms of system variables. The authors emphasize that their model for phospholipid assembly in apolar solvents is capable of accurately predicting the assembly response and morphology changes of phospholipids in bio-oils, enabling the tuning of lipid-based microemulsion systems and their adsorption. The introduction also highlights the importance of bio-based microemulsions in various fields such as biology, pharmaceuticals, cosmetics, food additives, and drug delivery systems. The ternary mixtures of phospholipids, water, and low-polarity organic solvents are particularly relevant and have been extensively studied due to their high water sensitivity and the ability to form reverse micellar structures. The water content in the system plays a crucial role in controlling the characteristics of microemulsions and reverse micellar systems, affecting surfactant aggregation, micelle swelling, and phase separation. The introduction mentions the gap in understanding the assembly response of phospholipids in bio-oils, particularly triglycerides, and the need for computational modeling to address this gap. The introduction concludes by highlighting the challenges in characterizing microemulsion phase behavior and microscale structural features, as well as the importance of molecular modeling methods in accessing surfactant aggregation and dynamics. The DPD modeling approach is described as a versatile tool that allows for the examination of large-scale assembly and dynamics, providing predictions for assembly morphologies and adsorption phases. The authors further discuss the parametrization and verification of the DPD model and the potential for extending the approach to other systems. Presents the assembly phase diagram of phospholipids in bio-oil solvents. It demonstrates the transition from reverse micellar structures to network-like structures and lamellar phases as the water content and phospholipid concentration vary. The water-to-DPPC ratio plays a crucial role in determining the assembly behavior and morphology of the assembled structures. Overall, the phase diagram provides valuable insights into the self-assembly of phospholipids in bio-oil solvents and can be used to guide the design of lipid-based microemulsion systems. Figure 2 in the paper shows the assembly phase diagram for the phospholipid, DPPC, in triglyceride solvent as a function of phospholipid concentration and water to DPPC ratio. The figure includes representative visualizations of each assembly phase. The phase diagram reveals the transitions between different assembly morphologies as a function of system variables. At low water content, reverse micellar structures are observed, which transition to network-like structures and various lamellar phases with increasing water content. The phase diagram provides important information about the behavior of the phospholipid assembly in the ternary system. The significance of Figure 2 is that it demonstrates the ability of the DPD model to accurately predict the large-scale assembly response and morphology changes of phospholipids in apolar solvents. The model's parametrization and verification information enable its extension to other systems. The phase diagram provides insights into the tuning of lipid-based microemulsion systems and their adsorption properties. Other figures that may be useful to discuss in relation to this paper include Figure 3, which shows the phase behavior of the ternary system, and Figures 7 and 8, which demonstrate the adsorption of DPPC on adsorbents of differing polarity. These figures provide further insights into the behavior of the phospholipid assembly and its interaction with different surfaces. Figure 3 in the paper shows the assembly phase diagram for the DPPC, triglyceride, water ternary system as a function of DPPC concentration and water to DPPC ratio. The figure displays different assembly phases, including reverse micellar structures, network-like structures, and lamellar structures, as well as the transitions between them. The water content and DPPC concentration play a crucial role in determining the morphology and organization of the phospholipid assembly in the bulk phase. The significance of Figure 3 to the paper is that it provides a comprehensive understanding of the assembly behavior of phospholipids in bio-oils. The phase diagram allows researchers to predict and control the large-scale assembly response and morphology changes of phospholipids in the system based on the water content and DPPC concentration. Additionally, the figure helps in the design of lipid-based microemulsion systems and their adsorption properties. It provides insights into the tunability of these systems and their potential applications in various fields, such as pharmaceutics, cosmetics, food additives, and drug delivery systems. Other figures that are useful to discuss in relation to this paper are Figure 4, which shows the size distribution of DPPC aggregates at different concentrations, and Figure 7, which presents the density maps of DPPC head groups on adsorbent surfaces of different hydrophilicity. These figures provide additional evidence and insights into the assembly behavior and adsorption properties of DPPC in the system. Figure 4 of the paper shows the adsorption response of dipalmitoylphosphatidylcholine, DPPC, phospholipids to smooth adsorbate surfaces of varying polarity. The figure displays the density of adsorbed DPPC head groups on the surface as a function of surface hydrophilicity and water to DPPC ratio. The results indicate that on hydrophobic surfaces, DPPC adsorption increases with DPPC concentration and surface hydrophilicity. On hydrophilic surfaces, DPPC forms a monolayer with coverage dependent on DPPC concentration. The presence of water acts as a competing adsorbate, leading to a depletion of DPPC adsorption on hydrophilic surfaces as water content increases. The significance of these findings is that the DPD model accurately predicts the adsorption response of phospholipids in terms of surface hydrophilicity and water concentration. The model provides insights into the competing adsorption behavior of phospholipids and water, and the different adsorption regimes observed on hydrophobic and hydrophilic surfaces. This information is valuable for understanding the interaction between phospholipids and surfaces in various applications, such as bio-oils processing and interfacial lubrication. The results also highlight the importance of water in determining the adsorption behavior and morphology of phospholipids on surfaces. Figure 5 in the paper shows the radial distribution function, RDF, calculated between the DPPC heads and surface beads, as well as between the DPPC tails and surface beads. This figure is significant as it provides information about the spatial distribution of the DPPC molecules with respect to the adsorbent surface. The RDF curves show that on hydrophilic surfaces, the DPPC head groups gradually shift away from direct contact with the surface with increased surface hydrophilicity. On the other hand, the DPPC tails show direct adsorption with the hydrophobic surface. This indicates that on hydrophilic surfaces, a DPPC monolayer forms, while on hydrophobic surfaces, aggregates of DPPC molecules are present. The significance of this information is that it helps understand the adsorption behavior of DPPC molecules on surfaces of different polarity. It shows that the hydrophilicity of the surface plays a role in determining the adsorption mode of the phospholipids. Additionally, the RDF curves provide insights into the spatial arrangement of the DPPC molecules near the surface. This information can be useful in designing and controlling adsorption processes in systems involving phospholipids, such as drug delivery systems or surface coatings. It is worth noting that Figure 5 is just one of the figures in the paper, and other figures may also be relevant and provide further insights into the study. Figure 6 in the paper shows the radial distribution function, RDF, calculated between the DPPC, dipalmitoylphosphatidylcholine, head groups and the surface beads for adsorbent surfaces of differing hydrophobicity. The top panel of Figure 6 presents the RDF between the DPPC heads and the surface beads, while the bottom panel presents the RDF between the DPPC tails and the surface beads. The RDF curves provide information about the spatial distribution and ordering of the DPPC molecules with respect to the adsorbent surface. In the top panel, for hydrophilic surfaces, the RDF curve shows a peak at a distance close to the surface, indicating that the DPPC head groups are in close proximity to the surface. As the hydrophobicity of the surface increases, the peak shifts away from the surface, indicating a decrease in the adsorption of DPPC head groups. In the bottom panel, the RDF curves for the DPPC tails show a peak at a distance close to the surface for hydrophobic surfaces, indicating that the tails are in close proximity to the surface. On hydrophilic surfaces, the tail peak shifts away from the surface, indicating a decrease in the adsorption of DPPC tails. The significance of Figure 6 is that it provides insights into the adsorption behavior of DPPC on surfaces of different hydrophobicity. The RDF curves show how the adsorption of DPPC head groups and tails varies with the hydrophobicity of the surface. This information is important for understanding the interactions between phospholipids and different types of surfaces, which has implications for various applications such as drug delivery systems and surface coatings. Overall, the results from Figure 6 suggest that the adsorption of DPPC on surfaces is influenced by both the hydrophobicity of the surface and the hydration level of the system. This information can be used to design surfaces with desired properties for specific applications. Figure 7 in the paper shows the density maps of DPPC head group distribution on different adsorbent surfaces as a function of surface hydrophilicity and water to DPPC ratio. The top panel of Figure 7 presents the density maps for hydrophilic, mica-like, adsorbent surfaces, while the bottom panel presents the density maps for hydrophobic, polyethylene-like, adsorbent surfaces. The density maps demonstrate the adsorption behavior of DPPC on surfaces of different hydrophilicity and the impact of water content on the adsorption. The significance of Figure 7 is that it provides insights into the adsorption response of DPPC on surfaces of varying polarity. The density maps reveal that on hydrophilic surfaces, DPPC forms a monolayer with higher surface coverage as the DPPC concentration increases. On hydrophobic surfaces, DPPC adsorbs as aggregates, and the surface coverage increases with the addition of water. The figure highlights the role of surface hydrophilicity and water content in determining the adsorption behavior of DPPC. The results and conclusions related to Figure 7 indicate that the adsorption of DPPC is influenced by the surface hydrophilicity and water content. Hydrophilic surfaces promote monolayer formation, while hydrophobic surfaces lead to aggregate adsorption. Water acts as a competing adsorbent on hydrophilic surfaces but also promotes aggregate growth and adsorption on hydrophobic surfaces. These findings have implications for understanding and designing lipid-based microemulsion systems and their adsorption properties. Figure 8 shows the adsorption of DPPC, dipalmitoylphosphatidylcholine, on adsorbent surfaces of differing polarity. The top panel of Figure 8 presents the surface density of adsorbed DPPC, while the bottom panel shows the corresponding data for adsorbed water molecules. The hydrophilicity of the adsorbent surfaces is represented by the parameter, L, with L equals 0 corresponding to a hydrophobic surface, similar to polyethylene, and L equals 0.1 corresponding to a hydrophilic surface, similar to mica. On hydrophilic surfaces, DPPC forms a monolayer with higher surface coverage at higher DPPC concentrations. The coverage saturates at around 0.2 square nanometers per DPPC lipid for a concentration of 100 m. On hydrophobic surfaces, DPPC forms aggregates that are loosely bound to the surface. The aggregates become more compact and closer to the surface as the DPPC concentration increases. The presence of water affects the adsorption behavior. On hydrophilic surfaces, water competes with DPPC for adsorption, resulting in a decrease in DPPC adsorption with increasing water content. On hydrophobic surfaces, water promotes the growth of DPPC aggregates and leads to increased adsorption of both DPPC and water. These results indicate that the adsorption behavior of DPPC is highly dependent on the polarity of the adsorbent surface and the presence of water. Hydrophilic surfaces favor the formation of a DPPC monolayer, while hydrophobic surfaces promote the formation of DPPC aggregates. The presence of water can either compete with DPPC for adsorption or enhance the adsorption of both DPPC and water. The significance of Figure 8 is that it provides valuable insights into the adsorption behavior of phospholipids in bio-oils and the role of surface polarity and hydration in determining the adsorption response. This information is important for understanding the behavior of phospholipids in biological systems as well as in technological applications such as drug delivery systems and cosmetics. Figure 9 in the paper shows the adsorption of DPPC, dipalmitoylphosphatidylcholine, on adsorbent surfaces of differing polarity. The x-axis represents the surface hydrophilicity parameter, while the y-axis represents the surface density of adsorbed DPPC. The figure includes two panels. The top panel shows the adsorption of DPPC head groups, while the bottom panel shows the adsorption of DPPC tails. The significance of Figure 9 is that it demonstrates the different adsorption regimes observed on hydrophilic and hydrophobic surfaces. On hydrophilic surfaces, the density of adsorbed DPPC increases with increasing DPPC concentration and surface hydrophilicity. This indicates the formation of a monolayer of DPPC on the surface. On hydrophobic surfaces, the density of adsorbed DPPC is lower and the DPPC aggregates are observed. The aggregates are less strongly bound to the hydrophobic surface and may exhibit different geometries, such as spherical or elongated ellipsoids. The results suggest that the adsorption of DPPC is influenced by both the surface hydrophilicity and the presence of water. On hydrophilic surfaces, water acts as a competing adsorbent and reduces the adsorption of DPPC. On hydrophobic surfaces, the presence of water promotes the growth of DPPC aggregates and enhances the adsorption of DPPC. Overall, Figure 9 provides insights into the adsorption behavior of DPPC in bio-oils and highlights the importance of surface polarity and water content in determining the adsorption response. These findings have implications for the design and engineering of lipid-based microemulsion systems and their adsorption properties. Figure 10 in the paper shows the surface density of adsorbed DPPC, dipalmitoylphosphatidylcholine, on a hydrophobic adsorbent surface as a function of the system water content. The x-axis represents the water to DPPC ratio, which indicates the relative amount of water compared to DPPC molecules in the system. The y-axis represents the surface density of adsorbed DPPC, indicating the amount of DPPC molecules that have attached to the surface. The significance of Figure 10 is that it demonstrates the effect of water on the adsorption behavior of DPPC on a hydrophobic surface. It shows that as the water content increases, the surface density of adsorbed DPPC also increases. This suggests that water promotes the adsorption of DPPC on the hydrophobic surface. The increase in adsorption is likely due to the water molecules competing with DPPC for surface attachment sites. Overall, Figure 10 provides important insights into the role of water in the adsorption behavior of phospholipids, which is relevant for understanding the assembly and behavior of phospholipids in bio-oils and other systems. In this scientific paper, the authors use dissipative particle dynamics (DPD) simulations to investigate the assembly and adsorption response of a ternary bio-oil phospholipid water system. They first validate their model by comparing the simulated phase diagrams with experimental data. They find that the presence of water affects the assembly morphology, with the formation of reverse micelles, network-like structures, and lamellar phases depending on the water content and phospholipid concentration. They also study the adsorption of phospholipids on surfaces of varying hydrophilicity and find two distinct adsorption regimes: monolayer formation on hydrophilic surfaces and aggregate adsorption on hydrophobic surfaces. The presence of water acts as a competing adsorbent on hydrophilic surfaces but promotes aggregate growth and adsorption of admicelles on hydrophobic surfaces. The authors conclude that the DPD model accurately predicts the large-scale assembly response and adsorption behavior of phospholipids in bio-oils, providing insights into the design of lipid-based microemulsion systems and their adsorption properties. If you are an author or copyright holder for the work presented in this video and you have any issue with the existence or contents of this video, please let me know.